Okay, merge sort. The second sorting algorithm is going to be called merge sort. Quick sort's average case. Worst case, it's n squared. Merge sort is always n log n. But hopefully y'all detect the one problem with merge sort when we get to it. But first off, this is nice. It's n log n, right? So we should, now we can actually guarantee that the sorting will occur in a certain amount of time, or at least in a faster time than our previous 3. So merge sort, it's straight up divide and conquer. You partition, first you partition everything into 2 sublists, and you keep partitioning until you have 2 lists of 1 element. You know that a list with 1 element is sorted. So then you start, once you've divided it all out, you start merging all the elements together. Notice the difference here with quicksort. Quicksort first found the element, put it where it needed to be, and then divided. Merge sort's going to divide everything and then put the elements together as they should be. So they're kind of the opposite. They're doing the same thing, just in a different order. I think they came up with a really good picture of this. All right. So there's the divide first off, and then there's the merge afterwards. So the divide breaks it up in half. Yeah, roughly up in half. Okay, good. They have 8 elements, so they're going to definitely do it in half. And they keep dividing in half until all lists have only 1 element. So on the left, you notice you have the 35 and the 28. When you merge that, 28 goes first, then 35, 18, 45, you're good. 62, 48, 48 goes first. 30, 38, that goes first. Now, they take these 2 lists and they merge it together. How can you do a merge in O of n time when you know the 2 lists are already sorted?
Just add it to where we did.
What's that?
Yeah, add to the end, like one sorted and the other one sorted, but you know they don't overlap. You just add it to the end.
Let's do a big example on the board.
Well, they should.
All right, give me, let's see, 4 numbers in ascending order.
1, 2, 3, 7.
we already determined 7 was not.
Yeah, that's right. We can't use 7.
All right, 24, 56, 87, 2, 9,
5G, we get 5G.
43, and 9001. All right. You want to create a list that is sorted in O of n time, where n is the number of elements. How do we go about doing that? What's going to be the first element? 1. All right. What's going to be the next one? 2. Hold on a second here. So you did 1. We're going to have our pointer go to 24, and this pointer's still at 2. You ask if 2 is less than 24, it is, so you put it there. You move this guy over. Oops. Is 9, or actually you would say, is 24 less than 9? No, so we're going to put the 9 here. Move this pointer over. Is 24 less than 43? So he's going to go next. Is 56 less than 43? No, so who goes next? 43. All right. Is 56 less than 9001?
Yeah.
All right. Yeah. That was good. 87 less than 9001? Yes. And now that this list is past its length, you just add everything else from the other list. Is that list sorted? Yep. How long did that take? No, this one routine right here. Just O of n, because I just went through the size of the list. I didn't have to go back and forth or anything. Yes?
So why are you assuming that they're in ascending order?
Because we have partitioned them up so they are. Look, if a list is 1 element, it's sorted, right?
Yeah.
Yeah, so we merged those by using this algorithm into a list of 2 elements. We did that all the way down. Now that we then know that all these lists have to be sorted because we just merged two. You know, lists with just one element into an element of two. Then you take those two lists, they're sorted, so you merge them again.
Okay, so the O(n) part is the merging of two sorted lists, and
Mhm.
the log of log base 2(n) is the divided.
Yes. Notice at each level, we did O of n comparisons. We just broke them up against a long array or part of it. And then the question is, how many of these O of n operations do we do? Log of n. Thinking, how many levels are here? Well, there's 8. How many levels are down here? 3. Okay, that kind of came out nicely. Of course, notice that your divide also broke it up into 3 as well. So it's actually it's n log n plus n log n, which is just big O of n log n. All right. Do we get to see any code with this? Okay, we get to see the general algorithm. Great.
I guess that's not really as helpful if you have like 50 million.
Maybe. Does anyone see the problem with merge sort? Kind of showed it up on the board. You have to what? You have to have two functions. If you're doing recursively, yeah, you want to have two functions. That's not a problem.
What if the array, for example, has an odd number of elements?
Right, so it just wouldn't divide out perfectly, but it'd still be n log
But
n.
then if you have a whole bunch of stuff, like, you know, big close to 50 million, then you have 50 million small individual.
Yeah, yeah. I mean, that's fine.
If you're making new arrays every time, a lot.
There we go. That's the problem.
That's what I'm
That's
talking
one.
Look at, you notice in the board, you had, up here you had 2 arrays, and I had to make a third array. I couldn't just merge them together. I had to come up with the second array, put the elements in. So the problem with merge sort is it requires twice as much memory that you have, because you need to create a whole new array every time. Yeah, so that's a problem. It's still n log n though, it just takes twice as much memory. Quicksort is called in place because you didn't have to allocate any more memory, and it was still on average n log n. See how there's a trade-off now? Yeah. Kind of have to choose.
pretty big thing.
Wait, can't you just make it not require that second or the third array?
All right, how?
By, so if we're going through it, so 1 is less than 2, so then you just move, well then there wouldn't be a little thing, or would it?
Oh yeah, if you had to
Well,
shift
wait,
all
is
these
this a
down.
linked list or array?
Huh, that's even a better question. Right now we're doing an array.
Okay.
Now if it was a linked list, would we need to allocate any more memory?
No.
No, we just do our fun pointer changes and hook it all up. So a linked list can be sorted in n log n without any extra memory. That's a good point. Even more trade-offs. Because what's the problem with the linked list? Hard.
So I still have yet to understand.
You can't randomly access. Yeah, you can't just jump around in a linked list because you have to iterate through it. While an array, you can jump around.
Can you make a function to do that now?
Yes, but you still have to iterate through the whole list behind the scenes. So that means that getting to a random location is an O of n operation as opposed to an array, which is an O of 1 operation. Trade-offs.
Yeah, but for these functions, you wouldn't need to get to random locations, right?
Correct. So for sorting, it's still n log n, but after you sorted it, you may need to do something else with it. If you need to be able to jump in a random location, you're probably going to want an array. But if you just need to go through it again, then a linked list would be just fine.
Well, if you, well, I guess then this would require more memory. I was saying, if you wanted to, after sort it, then you can just iterate through it, setting a array equal to each.
Right, so you could allocate a new array, copy
And then-
everything over. Sure.
And then delete the.
Linked list.
Yeah.
Yeah, so that can be done as well, but then you've just used twice as much memory. But again, not a bad trade-off. That still might be a good thing. It depends. It just depends on your situation. All right. If the list of a size is greater than 1, all right, we did this tutorially. Let's go look at it. You just keep dividing the list into 2 sublists, and you call merge sort on the first sublist, and that's going to go back and call itself. So remember, this is a recursive algorithm. And it's going to keep dividing the sublist. Merge sort the first list, go back up, divide it, keep dividing until it's less equal or 1. Then that one's going to return. You're going to do the same thing on the second list, and then you'll finally merge the first list and the second list. All right. Hey, look, let's do, what are they going to do with the linked list? So, unsorted list, they got a head, middle, and current. They find where the middle is, and then they basically chop it off. Notice you have head and other head, and that's probably going to recurse on down. So you've done it with this one up here. You can call merge sort again, so that you would have a smaller list, smaller list, smaller list until you had just 2 elements. But let's go ahead and take the idea of merging 2 linked lists. This is actually fairly straightforward, or I'm sorry, I shouldn't say that. Merging 2 sublists that are linked list. You have a first pointer, second pointer. Do they show you what happens? Oh, okay, great. So you're going to have, what they're going to do is, they're going to have new head point to what's less, which is the 18, and then increment first. What do you think is going to happen next in this algorithm? Which 2 elements are they going to compare? Which one? Right, and those values are, so they compare 25 and 20, right? Which one's less? 20. So what's last merge going to point to? 20, and first 2 is going to point to 30. Let's see if they do that. Perfect. Do you see what happened there? Updated that to point down to the 20. Notice the increment last merge as well, because you need to know what's at the tail of this thing. So now, what are they going to compare? 25 and 30. What's going to happen?
25 is less. Was it one last merge to 25?
Yep.
20 to 25 as well. And then the first one to 65.
You got it. So last merge is going to go up to 25. First is then going to point over to 65. Oh, they don't even show it afterwards. Okay. But you see how it just keeps going on down the line until the whole list is sorted? Hopefully. Okay. And this is nice because it didn't have to use an extra piece of memory. All right, they're going to do analysis of merge sort. We did this pictorially. They go through, I guess, a somewhat more rigorous one, but a list L with n elements. Suppose n's a power of 2, so that n equals to the m for some integer. All right, that's great. There are going to be m number of recursive levels. That's what we're talking about when you divide in half. There's really just log base n calls or levels to the algorithm. Wow, they're going to do it more pictorially than I did. Yeah, may have 8 elements, then 4, then 2, then 1. The whole point of this is that the number of levels is log of n. Each time you're doing n comparisons, which max number of comparisons at level k. If you're going to compare everything is O of n. And then, of course, the, let's see, maximum number of comparisons, each level is n. The maximum number of levels is, looks like they said, where's log of n? Yeah, key comparisons, worst case, n log n, that's right. Yeah, n log n. Worst case. A is average, is what they're trying to use here. All right, n log n. Oh, okay, wow, that's it. All right, so now I'm going to go ahead and